In this lecture, we'll be looking at arrays, how we can convert arrays into the MIPS instruction. That means when we have arrays in our high-level instruction, how we can convert them into MIPS instruction. Let's say we have an instruction, a high-level instruction, something like this: x is equal to y 5 plus 20. Now, how can we convert this into assembly code, MIPS assembly code? So, before we can start converting it into MIPS assembly code, what we need to know the register assigned to each of these variables. This x, the array y, and 20 is integer, so we can directly use it. Now, we need to know which register holding the value of x, and in case of array we need to know where the base register is, where the base value of this array is, that means in which register. So for simplicity, let's assume that x is in register 10 and base address of this array is in register 11. Now, what is base address? Base address is, if this is our memory layout, now let's say from this position to this position is the place where memory stores array y. So, this is the address where y0 is, and then other elements are there, other array elements. So, this address is can be called as base address for array y0. Now we need to know the base address, because if we know the base address, only then we can find the memory address of any specific array element. Let's say we need to find the address of y4. How can we do that? To do that, what we need to do, or we need to know, is what is the base address. That means the starting address of this array. If we know the starting address, so let's say the starting address of this array is let's say 100. 100 is the starting address. So this address, this is 100. This is 100 memory location. Now, how can we find the memory address of array element y4? To do that, what do we need to do? We need to add with this base address, what? We need to multiply this index, that is 4, multiplied by 4, which is 116. That means 116 memory address is the starting memory address of array element 4, that means y4. Now, why did I multiply this one with 4? Because we already have discussed in our previous video lectures that for any element we assign one word size of memory to each element. So, array element y0 array element will have one word of memory. Similarly, y1 will have the following one word, y2 will have the after that one word, and then all the elements will continue like that. So one word is physically, if we consider the first word, then the word zero would be byte 0 till byte 3. So word 1 would be from byte 4 to byte 7 and so on. These are all physical location and these are our logical addressing, just because these word address can change. I mean, this word address means this word length can change. We are considering this for 32-bit because the architecture that we are studying is 32-bit. But in case of 64-bit architecture, this would be 64. So we need to come up with these numbers which would represent 64. But these are physical addressing, byte 0 by up to byte 3. So what is the starting address of word 1? Starting address of word 1 is 4. That means if we are to find, let's say, array element 1, then we need to multiply 1 into 1 by 4. So this is how we are getting this. Now let's generate the MIPS address of this this instruction. So as we have already declared that X will be in register 10 and Y array, the base address of Y array is in register 11 and 20 is our integer. Now how can we do that? So to do it, what we need to do, just see in this part, we just need to perform an addition. Addition of what? Addition of whatever the value y5 contain with 20. This is what we need to do. So but this is in memory location, and the architecture that we are studying are stored program architecture. That means we need to bring the value from memory into the register. First of all, we need to load this value from the memory into the register. So let's perform that task. So we would execute load operation, and let's say the destination register for this load is register 5. And then what do we need to do? We need to write an integer which is multiple of 4. So what is the index that we are looking for? Y5. So what this would be? This would be 20. How? See, we are multiplying it by 4. So whatever the index that we have here, we just multiply it by 4. So we'll have 20 here. And now where the base address is? Base address is in register 11. What this instruction does, this instruction performs two operations. One, after the arithmetic operation here, that means operation something like this. After the arithmetic operation, this instruction gets the target memory address. Once it gets the target memory address, then it goes to that memory address and brings the value that is stored on that memory address to the destination register, that is in this case, which is 5. So now we have the value of Y5 in register 5. Now our job is to add this part. So how can we do that? We can do it like this: add I, and then let's reuse this register. Reuse this register 5. So 5, then again 5, and we have this 20. Sorry. We cannot reuse this register. We cannot. That would not. That will not serve our purpose. So what we'll do, we'll write register 10. In that way, we are directly storing the result in this register. So this is how we save the value of this addition in register 5 in X, which in this case is in register 10. See, register 5 contains the value of y5. So we have that value and this is 20. So we perform the addition. This is I-type operation. So we just perform the addition, and after the addition we store the result in register 10, which is actually our x. Now this is how the operation takes place. Now there is another thing that you need to know here, and that is really important for exam, is uh, you need to, even though this is just one instruction, uh, you will have sequence of instructions, and from those instructions you need to identify each individual instructions, and then you need to encode it. We already have seen how we can encode the instruction, but before encoding you need to know what is the type of the instruction. So just for simplicity of this two instructions, I'll explain that with more instructions in later videos, but just for the sake of this example, this instruction, this is our I-type instruction, and this is again I-type instruction. In this I-type instruction, this one is our source and this one is our destination. Similarly, here this is our source, this is our constant or offset, and this part register 10 is our destination. So what we need to do here? We need to generate the I-type instruction format for both these cases, and we have opcode here, opcode and opcode, which is 6-bit, and then we have RS and then RD or RTRD, it's up to you, and then we have offset, again RS, RD, offset. Now, what is our opcode? As I said, that we do not have to be worried about opcode. So let's just give 6 crosses here. And what is our RS? This 11. So RS is 11, 0, 1, 0, 1, 1. This is 11. And then destination is 5. So this is 0, 0, 1, 0, 1. This is 5, and the offset is 20. 20 means this is 16, 0, 1, 0, 0, and then rest of the value will be 0. Now this one is the encoded form of this load instruction. What about this one? Opcode, again, don't worry about the opcode, you will have it in the question, but if you don't, then just leave it like this. And then RS, our source is 5, so which is 0, 1, 0, sorry. This is 0, 0, 1, 0, 1. This is our 5, and then our destination is 10, which is 0, 1, 0, 1, 0, and our offset is 20, again 1, 0, 1, 0, 0, and then the rest is 0. So this part, this one is the encoded form of add I instruction. As I said, that we'll see an entire example on how we can encode when we will have combinations of instructions in later videos. This is just a glimpse of how we should approach that problem, how we should solve those problems.